I wanted to show you this little guy here. I mean, this guy is really cool. Math Antics, really cool website. He has lots of cool sound effects, and his videos go really fast. And so for 11 minutes, we'll review some basic square root stuff with this guy, Math Antics. Pretty cool stuff. Everyone can see that? So just watch this for a few moments.
Hi, welcome to Math Antics. In our last video, called Intro to Exponents, we learned that exponents, also called indices, are a special type of math operation. In this video, we're going to expand on what we know about exponents by learning about their inverse operations, which are called roots. That's kind of a strange name for a math operation, but it will make more sense in just a minute. First, let's review what we mean by inverse operations. In the video called What is Arithmetic, we learned that inverse operations are pairs of math operations that undo each other. For example, you can undo addition by doing subtraction. So addition and subtraction are inverse operations. Likewise, you can undo multiplication by doing division. So multiplication and division are inverse operations. As I mentioned, exponents have inverse operations also. There are operations that can undo them, and those operations are called roots. To see how roots and exponents work together to undo each other, let's look at the simple exponent 4 to the second power, or 4 squared. Previously, we learned that this is the same as 4 times 4, which equals 16. Doing this exponent meant going from 4 squared to 16. So now if we want to undo that with the root operation, that involves starting out with 16 and then somehow getting back to the 4, which is being raised to the second power. And you remember what that part of the original exponent is called? Yep, it's called the base. So doing a root operation is going to give us the base as our answer. And that helps us understand its name a little better. The words base and root have a similar meaning, especially if you think of a tree. The root is at the base of a tree. And that can help you remember how root operations work.
Right.
With a root operation, you start with the answer of an exponent and try to figure out what the base of that original exponent is. Okay, but how do we actually do that? How do we use a root operation to go backwards and figure out the base of the original exponent? Well, for starters, we need to know about a special math symbol that looks like this. And you guessed it, it's called the root sign. Whoa, dude! That math symbol looks totally radical, dude! It's like that division thingy, only way cooler! Ah, yes, that reminds me. The root sign is often referred to as the radical sign, and mathematicians use that term even before surfers did. And yes, it does look similar to the division sign, so it's really important not to get them confused. The root, or radical sign, is different from the division sign because instead of having a curved front, its front shape is like a check mark. The number that you want to take the root of goes under the sign like this. So when you see a number under a root or radical sign like this, you know you need to figure out the base of the original exponent. In this case, you need to figure out what number you can multiply together a certain number of times to get 16. Ah, but there's the catch. How many times? The answer we get from taking a root will depend on how many times that number would be multiplied together. That is, it depends on the power of the original exponent. So how do we know what that number is? Simple. The root symbol tells us. The root symbol actually includes the original power or exponent in it. What? You don't see it? Oh, that's because I didn't draw it in yet. And later in this video, you'll understand why. So let's put a little 2 right here above the checkmark part of the root symbol. And that 2 tells us that we need to figure out what number or base could be multiplied together 2 times in order to get 16. And if you remember your multiplication table, or if you just look at our original example here, you'll know that the answer to that is 4. Now do you see how the root operation is the inverse of the exponent operation? When doing the exponent, we asked, what do we get if we multiply 4 together 2 times? And the answer was 16. But when we did the root operation, we asked, what number could we multiply together 2 times to get 16? And the answer was 4. Great. Now that you understand how exponents and roots are related, we're going to look closer at how root operations work. To do that, we're going to change our root problem slightly. let's change the little 2 into a little 4. The first root was asking us to figure out what number we could multiply together 2 times to get 16. But this new root is asking us to figure out what number we could multiply together 4 times to get 16. That's a bit trickier, huh? Can you think of a number like that? Yep, the answer is 2. Because if you multiply 4 2's together, 2 times 2 times 2 times 2, you get 16. So the second root of 16 is 4, but the fourth root of 16 is 2. Both those roots were pretty easy to figure out, right? But unfortunately, figuring out roots in math...
Okay, let me just pause it for a second. Remember, one of the things he's been saying is that they're inverse operations. So if you rewrote this as 2 to the 4th, and you had the fourth root here, a radical cancels an exponent. So it's almost like this one cancels this one, and so you get 2. Make sense? So you're going to see more of these radicals later on in our course. Primarily in chapter 1, we're going to deal with the square root. And when you have the square root, we don't write the 2 in there. It's the default square root. I mean, it's the one that comes up all the time. So anyhow, just thought I'd add that in.
Can be much harder. For example, what if we had this problem instead? Root 3 of 16. That means we need to figure out what number we can multiply together 3 times to get 16. Can you think of a number like that? No. I can't either. And unfortunately, it's not easy to calculate what that number would be. Remember, even though this looks a little bit like the division symbol, this is not just division. You can't just divide 16 by 3 to get the answer. Roots are not the same as long division. So how do we calculate a root like this? Well, there are special algorithms that you can use to calculate just about any root, but they're kind of complicated, so we'll save those for a future video. Instead, I'm going to use a special root function on my calculator to get the answer. And on my calculator, the button for that root function looks like this. To use it, I first enter the number that I want to take the root of, which is 16. Next, I hit the root function button, and then I enter 3, so it knows that I want the third root of 16. Last, I hit the equal sign, and voila! The answer is 2.519842, and the decimal digits just keep on going forever. Wow! See what I mean about roots being hard to figure out? This is a really complicated decimal number, and you may even wonder if it's the right answer. Well, let's check. Based on what we know about exponents and roots, if we multiply this decimal number together 3 times, we should get 16, right? But to make it easier to check, let's just round the number off to 2 decimal places. Let's make it 2.52. If we multiply 2.52 together 3 times, in other words, if we take 2.52 to the third power, we'll get 16.003. Well, that's almost right. It's really close to 16, isn't it? The reason it's not exactly 16 is that we rounded the number off, which made it less accurate. But the more decimal digits we use, the closer we'll get to 16. In math, the vast majority of roots are complicated numbers like this, and they're hard to figure out unless you use a calculator or a special algorithm. That's the bad news. But the good news is that most of the time, the roots you'll be asked to do in your homework or on tests are the easy ones, the ones that have nice whole number answers. And usually, you'll only be asked to find the second or third roots of numbers. Do you remember in the last video, we learned that 2 and 3 are the most common exponents? So common, in fact, that they even had special names. Raising a number to the second power was called squaring it, and raising a number to the third power was called cubing it. Well, it's the same with roots. Since the roots 2 and 3 are the most common, they get special names also. The second root is called the square root, and the third root is called the cube root. In fact, the square root is so common that it's basically the default root, and its symbol even gets special treatment. Do you remember that when I first showed you the root symbol, I left out the index number that tells you what root to find? Well, whenever that number is left out, you can just assume that it's 2. In other words, the root symbol with no index number is always the square root. So if you want someone to find a different root, like cubed, or fourth, or fifth, then you need to include that number so they know which root to find. And even though square roots are the most common, They're not always easy to find. Most are still going to be big, long decimal numbers, except for the perfect squares. It's easier to find the square roots of the perfect squares because their answers can be found using the multiplication table. On the multiplication table, have you ever noticed that all the answers to problems where the same numbers being multiplied together are on the diagonal of the table? In other words, 2 times 2 equals 4, 3 times 3 equals 9, 4 times 4 equals 16, 5 times 5 equals 25, 6 times 6 equals 36, and so on. Well, those numbers are called the perfect squares because they're the answers you get when you square a whole number. And that means if you take the square root of a number along that diagonal, you get a nice whole number as your answer. The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4. The square root of 25 is 5, and so on. See what I mean? Those roots are really common, and they're also easy to figure out if you know your multiplication facts. So if you're new to exponents and roots, learning the perfect squares is the place to start. Once you understand how those exponents and roots work, you'll be ready to figure out tougher problems. Alright, so now you know how exponents are related to roots. They're inverse operations and they undo one another. And you also know that just like 2 and 3 are the most common exponents, the square root and the cube root are the most common roots. You also know that finding roots is usually not very easy. That's important to know so you don't get discouraged if you feel like it's hard to figure out what a certain root is. You're not alone. We think it's hard too, and would normally just use a calculator to find them. The good news is that some roots are easy to find, like the perfect squares, so be sure to focus on learning them first. And remember, to get good at math, you need to actually practice what you learn from watching videos, so be sure to do some exercise problems. And as always, thanks for watching Math Antics, and I'll see you next time. Learn more.
Alright, so that was meant to just be a little review, and most of that should have happened in Algebra 1. And, you know, that's why I have this little chart up here. If you forgot the square roots or you don't know them very well, use this chart. I would say everyone should know clear up through the 12s. Okay? You should know the square root of 144 is 12. Square root of 81 is 9. And so on and so forth. And same thing with squares. You should know the perfect squares. It's just going to make your life a little bit easier to do the math in this section. So one thing that he didn't cover in this lesson are the other properties of square roots. And so we're going to get into some of the properties of square roots. And that's what the first half of this lesson is going to be about as we get into this. And I'm going to show you some of the properties of square roots now and some of the rules that have been given to us over the eons of time, you know. We've dealt with it. So we're going to learn how to do this quadratic formula, and we're going to learn how to solve that equation because sometimes it does not factor. Can't always use the principle of zero products. So what to do then? So our objective, let's get started right here. If you're doing Cornell notes, you're welcome to write that down. You can also get it later on the YouTube video. So students will be able to find solutions to quadratic equations by using the square roots. No, we're gonna do a study guide for this eventually. I'll probably give it to you tomorrow because we're gonna just get started on it. So how can you use square roots to solve a quadratic equation? So one thing you should realize is that we have actually 2 square roots for a certain number. And let me try to explain how that works. We're going to end up with 2 square roots, a positive one and a negative one. And the positive one we often say is the principal one. In fact, when you use your calculator will automatically give you the principal square root. Like if you did the square root of 16, your calculator would say it's 4, like that. And that is true. But when we look at the original equation up here, like this, if we had 16, let's see, how would we say it? Let's say we had 16 is equal to r squared, like this. And what we'd like to do is the inverse operation. Well, what would happen is we would take a square root here and a square root here. And when we do this, we're going to have to write a plus or minus. And let me explain why there's a plus or minus in here. Let's go back just a few steps, and I'll show you why you have to have a plus or minus. Since this is an easy problem, I'm going to solve it by just using common mathematics arithmetic. What number times itself gives you 16? And you're going, oh, well, it's 4 times 4. That equals 16. And so one of the answers is r is equal to 4. But notice that negative 4 times negative 4 is also equal to 16. And therefore, we get r is equal to negative 4. You see? So whenever we do this square root here, and this is true for all square roots, we really need to put in a plus or minus. And that's why they have a plus or minus here. And the plus one is what we call the principal square root. And the other one's called the vice principal square root. Okay, just kidding. Alright, I made that up. Okay, so that I was just being funny. Okay, it's actually the other one does not have a special name for itself. It's just called the other one. So stupid. Okay, so anyhow, whenever we're solving equations, since you don't know it's a variable, and when you do a square root here, a square root here, we're going to need to put a plus or minus like that. Okay? Now, let's continue. Isn't this fun? So that little symbol on top is, like they said on the video, is sometimes called radical, and mathematicians had that word way before the surfers did, but it's a good word anyway. When the waves are big and pumping, we say, oh, it's radical out there. Or, you know, radical, dude. Okay, so let's continue. So now we're going to start studying some of the properties of square roots. These are some of the rules that you can do anytime you have a square root. So, like, for example, if you have the square root of 50, now you'll notice it would be nice if all the square roots were perfect squares. Like square root of 25 is easy. We can handle that. That's equal to 5. But like he said on the video, the vast majority of square roots are not perfect ones. And the idea behind these rules here is that we might say, hey, wait a second. I can split this up. The point is, I could split this up as the square root of 25 times the square root of 2. And that's because 2 times 25 is equal to 50. You see? And that's what this property is saying. You know, if you have two factors in here, you can split up the factors as separate square roots. Now that's advantageous because in this case, I can simplify square root of 50 and rewrite it as square root of 25 times square root of 2. But this one I know is 5. And so then I could write this as 5 square root 2. You see? So that's how, you know, it's like, why'd that just disappear all of a sudden? Okay, so anyhow, that's an important property. Well, we have other properties as well that we will be using. This one, for example, we could write that as square root of 9 times the square root of 2. Now, you might say, well, I could have written this as square root of 6 times the square root of 3 also. And indeed, you could have done that, you see? But here's the deal. The reason why we use this property is because we want to simplify things. So pick numbers that you can actually simplify. We know the square root of 9. We know that one, the square root of 9 is 3. And so the nice thing is that we no longer have this radical up there because we replaced this radical with something that's easier. Unfortunately, square root of 2 doesn't simplify. So we still have this. So even though we could have rewritten it this way, we choose not that one because that one didn't really simplify any further. So always pick numbers that can actually help you simplify the problem. Well, now we come down to this one. You can also do division. Yeah. Yeah. Yes. Don't hit him. She's a very nice lady.
Which your interpretation.
Hey, is the intercom working? Did you hear me? Oh, because you called and I said hello. Oh. Yeah. Okay, no problem. All right, fine. Destiny, they need you in the office. All right, so let's look at this property for a few moments. How does this one work? And so let's look here. Now, you see there's a little clue as to what we want to do here. You should say, well, hey, I know the square root of 25, and if this weren't written as a fraction, I could probably do it. So you could write this as the square root of 2 over the square root of 25. And see, that's what this property is saying. You can split up the fraction into two separate square roots. Now, the reason why we wanted to do that is because I know the square root of 25 is actually 5. And so then I have square root 2 over 5. You see? So all we're going to be practicing in the first half of this lesson are some properties of square roots. Okay? And so that's why if you know those square roots very well, you're going to have a clue as to what to do. Because almost always you're supposed to use those somehow. Okay, so let's continue. So you're going to have a bunch of these. Now, you want to rewrite this as a square root times a square root, and I'll let you think about this yourself for a second. What are some numbers that we should use? Well, we could use 10 and 8, right? But do you see, is 10 or 8, is that a perfect square? It's better to use a perfect square instead. So quickly in your head you're thinking about the perfect squares and you're going, well, 1 squared is equal to 1, 2 squared is equal to 4, and 3 squared is equal to 9. And so you're looking for some factors, a times b, and what you're hoping is that some of them are perfect squares. Like if you do 4 squared, you get 16. And if you do 5 squared, you get 25. Do you guys see any factors in 80 that are on this list yet? 6 squared equals 36. 7 squared, 49. And so on. 8 squared, 64. Okay, well, here's the thing. I don't know about you, but I see one that's on the list already. Which one is it? Well, it's that one. I just happen to know that 80, it's equal to 16 times 5. So what that means then is that I could write this as 16 square root of 16 times the square root of 5. Now I chose those numbers, and there were many that I could have chosen from, like I could have done 10 times 8, but neither one of those is a perfect square. Now I could have also chosen 4 times 20, right? And 4 is a perfect square. I could have used that one. But 16 is bigger than 4, so I think I'll get more progress this way. Square root of 16 is 4. And then I have this square root 5 still. Okay? So you'll notice that if you use our calculators, your calculator will do this step for you also. Okay? So if you guys really stink at doing square roots, the good news is that the calculator will help you. Okay? And again, if you need to check out a calculator, just leave your ID up here Remember also that all I have is a classroom set, so you can't take them home. But if you're certainly welcome to use them during my class, and I can show you that at a later time. So anyhow, like I said, the first part of this assignment has to do with these properties of square roots. Okay? Alright, let's try that one. Okay, so another property or strategy here is that we could recombine into one square root. And you'll notice, like right now, we're kind of helpless because I don't know the square root of 6. That's not a common one. Square root of 21 is not a common one either. But when I combine them into one, remember I can combine them into one. Square root of a times b, I could do that, is equal to the square root of a times the square root of b. Okay? So I could take this, take the two separate square roots and recombine them into one, like that. And so sometimes it's advantageous to do that. Well, then what's 6 times 21? If I do that in my calculator, I think it's like 126. Is it? So just verify. Okay, so 126. 126. And now that's not a perfect square either. But you know what I noticed? I just now noticed this. Check this out. I know that this is 3 times 2, right? That's 6. And I know that one's 3 times 7. Because the 3 came up twice, I know that once I recombine it, there's going to be a 9 in there. Does that make sense? You guys all sort of see that? So if you take 126 and divide it by 9, it should go in evenly. And it does. That's 9 times 14. So now what I want to do is re-split them up into this combination instead of the original combination. Does that make sense? And so now I want to write this as the square root of 9 times the square root of 14. And I did that because I know the square root of 9 is 3, and now I have 3 square root 14. Okay? Alright, so these, again, all you're going to be doing in these first couple problems is practice using these properties of square roots to simplify. And again, if you kind of stink at this stuff and it doesn't really bother me if you want to use a calculator to do this. The calculator can do just fine. If you put this in your calculator, it would have given you that answer directly. Might be faster for some of you guys. What I want you guys to do eventually is focus on solving the quadratic equation. So this portion is kind of a review. Alright, well, so let's take a look at this one now. The property of square root says, hey, you can split this up into the square root of 4 divided by the square root of 81. And these are both perfect squares. So that means this is equal to 2 divided by 9. And so that one was kind of easy. Any questions so far? Are you guys getting this? How about this one? Once again, we can split up the fraction into 2 separate square roots. And that's kind of advantageous because I know the square root of 16. That's one of those perfect squares. And let me just show you again how the inverse operations work here. I think it's helpful. So the one way you can write this expression is like this. You know that that's a perfect square, right? Well, square root, so you could write this as 4 squared. The index on a square would be a 2. And here's how the inverse operations work. An exponent cancels with the square root. So basically what happens here is the square root cancels with that 2, and so this portion is 4. Okay? And I don't know if that's helpful or not, but it might help some of you guys understand how they work a little bit better. Unfortunately, that's not a perfect square, so that we just leave it as it is. We only simplify it if there's a perfect square root in there. Does that make sense? Anyone falling asleep yet? All right, so if we had time, we would go through all these right now. But I think you could practice some of those. You'll have some of those on the study guide when we get to it. And so we will also do some of those on the homework assignment when we get to it. All right, now let me move on to this idea here. One of the rules that has evolved over the years is this one. For whatever reason, mathematicians don't like it if there's a square root in the denominator. So that's what we have to do here. We have to get rid of any square roots in the denominator. So like for example, if you have 3 over the square root of 2, that's what we're talking about. It's considered bad mathematics if you have a square root in the denominator. It just makes things more confusing as far as communication. So what we do is we multiply the numerator and the denominator by the same number, and we try to get rid of this square root. Now, you probably know this idea already. You've done it with fractions all the time. If you had 1, you could multiply by 5 over 5, and this becomes 5 over 5, right? And so it's still equal to 1, right? And you have 1 here, which is equal to that, right? So you're allowed to multiply any number by a number divided by itself. So you could take 2 and multiply it by 4 over 4, and in this case you get 8 over 4, and that of course is equal to 2. And see, so you're always allowed to multiply by a number divided by itself. Make sense? And it's still equivalent. Well, that's what we're going to do here, except for the number that I'm going to choose this time is identical to that one. Square root of 2, square root of 2. And that is often what we call the conjugate. We'll understand that a little bit more as we get into the other chapters in Algebra 2. But I could have chosen square root 3, I could have chosen a bunch of other square roots, but I chose square root 2 because now this is a perfect square. Watch what happens. In the numerator, I have 3 square root 2. But in the denominator, I now have the square root of 4. You see? And I know the square root of 4 is 2. So one thing you should observe is anytime you multiply a square root by itself, you get the number on the inside. Okay? And you might say, well, why is that? Well, let me review it real quick. If you take the square root of 5 and you multiply it by the square root of 5, what you could say is that it's 5 squared. And then you take the square root of that. Well, remember what happens? The index for a square root is a 2. And remember, roots are inverse operations of exponents. So this square root cancels out that one, and so it gives you 5. So anytime a square root is multiplied by itself, you simply get the number on the inside. And so that's the idea on how to get rid of a square root that's in the denominator. Just multiply it by itself in the numerator and denominator. This is the same thing as multiplying by 1. It will be equivalent still, just like I showed you up here. If you multiply by 1, it's still going to be equivalent. Even though your fraction changed, like I started off with 2 here, I then wrote it as 8 over 4, it's still equivalent to 2. You see? And so the new fraction that I've come up with, 3 square root 2, this one is equivalent to what I originally had up here. That's the idea. But now it's not written with the square root 2 in the bottom. Does that sort of make sense? And so the idea is to get rid of the square roots in the denominator. So if you're doing problems on homework and you still have a square root in the denominator, it's probably going to be marked half wrong. You didn't finish it. Does that make sense? You're going to be always expected to get rid of a square root if it's in the denominator. So let's do a few more of these so you get the idea. Okay, so what I could do, I could start out by writing this as square root 5. over the square root of 2. But Mr. Muscle told me I can't have square root 2 in the denominator, so I have to multiply by square root 2 and square root 2 here. Well, this would give me the square root of 2 squared. And this up here would give me the square root of 10, right? Now, I've been told that the square root and squares are inverse operations, so they cancel each other. So that means I have a 2 down here now. And in the numerator I have square root 10. Okay? Alright. What I should do is stop right here, and I should have my study guide printed out for you. So since I don't have the study guide printed out for you, what I'd like you to do is spend the last 10 minutes, and what I want you to do is I want you to start 1.5. Okay, I want you to start it. The first problems on 1.5 are just like the ones we've been doing. And then tomorrow I'll give you the study guide, and we can work on the study guide and try and finish it up. It's going to take me another day or two to finish this all up, okay? So let's stop right here.